In this video, we will be looking at equivalent trig expressions, and specifically, we will be looking at reflection identities, related angle identities, and cofunction or correlated angle identities. So we're going to start with our reflection identities. And the first one is sine of negative x is equal to, and we have to find an equivalent expression. And I'm going to start off with a sketch here. So when I have sine of negative x, that negative is like your k value, that's -1, which means it's a reflected sine function specifically over the y-axis. Here's what the base sine function looks like. And if it's reflected over the y-axis, this is what it will look like. And if I extend it, it looks something like this. So a reflection over the y-axis actually looks the same as reflecting the base function over the x-axis. With that in mind, I can say sine of negative x is the same as negative sine x. So whether I reflect over the x or the y-axis for sine, you'll end up with the same reflected function. Now let's do the same thing for cos. Here is my base function for cos. If it is reflected over the y-axis, this is what we will have. And it's just a continuation. So if I reflect over the y-axis, there is no change in the cos function, because if I were to just continue, it's just overlapping. So cos of negative x is the same thing as just cos x. And now let's look at our tan function. So the original tan function has asymptotes at pi over 2. So let's say pi over 2 is here, 3 pi over 2, and then 2 pi is there. So your tan function looks something like this, just from 0 to 2 pi. And if I were to reflect that over the y-axis, this would now go here. Our asymptotes will still be the same. And now I'll have something like this. And if I were to just continue that, you'll notice that if I reflect over the y-axis, it's the same thing as reflecting over the x-axis, just like what we saw with sine. So tan of negative x is equivalent to negative tan x. And the exact same reflection identities will apply to the reciprocals. So cosecant, who's the reciprocal of sine, when it's reflected over the y-axis, it's going to be the same as being reflected over the x-axis, just like with sine. And for secant, who's the reciprocal of cos, if I reflect over the y-axis, it will not make a difference. It will look like the same secant graph, just like with cos. And for cotangent, a reflection over the y-axis will be the same as a reflection over the x-axis, just like we saw with tan x just now. And those are your 6 reflection identities. And these are very just visual identities, thinking about the reflections and that original base function. Now we can move on to the related angle identities. And these ones use your knowledge of the cast rule. And they are identities that you actually have seen in the past, they just weren't called related angle identities. So in quadrant 1, we know our angle starts from the positive x-axis, and if theta is in quadrant 1, all of our angles are positive, we know that. In quadrant 2, here is angle theta. And in that quadrant, if x is acting like that related acute angle, so instead of alpha, I'm going to use x here, then theta is just equal to pi minus x. So you'll notice the first 3 identities we do are going to be about sine of pi minus x. So sine in quadrant 2, how is it related to sine x in quadrant 1? Well, we know with our CAST rule, C-A-S-T, that in quadrant 2, only sine is positive because the opposite and the hypotenuse are both positive here, whereas the adjacent side is negative because we're on the negative x-axis, so cos and tan will be negative. With that in mind, sine of that angle in quadrant 2 will be equivalent to sine x, that's in quadrant 1, because remember x is the angle right here between the x-axis and the terminal arm. It's that related acute angle. Cos, however, will be the same ratio as cos x, but it will be the negative version. And same thing with tan. Now, when we move to quadrant 3, here's our quadrant 3 angle. And if that is theta, and x is this little helper acute angle, theta is equal to pi plus x. And we are now in quadrant 3, where only the tan ratio is positive because here both the opposite and adjacent sides are negative, which means sine and cos will be negative. But because tan is opposite over adjacent, that's going to be negative divided by negative, it will have a positive ratio overall. So sine of pi plus x will be the same as the sine x ratio from quadrant 1, but negative. Same for cos, the negative version. Whereas for tan, the ratio in quadrant 3 will be copy-paste to quadrant 1, including that positive sign. Finally, we go to quadrant 4. Here's our little helper x angle, the related acute angle. Here, theta is 2 pi subtract x. Just a reminder that when you're finding these angles, it's always with reference to the x-axis because our little related acute angle is glued to the x-axis, not the y. And now we're in quadrant 4, where only cos is positive because here our opposite side is negative, but only the adjacent is positive. So only cos will be positive here. Sine and tan that rely on the opposite side will be negative. So that means sine of 2 pi minus x is equivalent to negative sine x. For cos, it's just going to be the positive version, and for tan, the negative. So this is really just your prior knowledge, just kind of standardized in these related angle identities. These are not new though. And these same ideas apply to the reciprocals. So in quadrant 2, where we're in S, only the reciprocal of sine will be positive. So that's cosecant. Whereas secant will be negative and cotangent will be negative as well. In quadrant 3, we're in tan's quadrant. So cosecant will be negative, secant will be negative, but cotangent will be the positive ratio. And quadrant 4, cos's quadrant, so only its reciprocal secant will be positive. And there we are. These are your related angle identities. These identities are with reference to the acute angle that is glued to the x-axis. So these angles are formed by the addition or subtraction from pi or 2 pi. We do not touch pi over 2 or 3 pi over 2. That does, however, lead us into the cofunction identities or complementary identities or also correlated identities. So we're going to start with this right triangle here. I have the length of x, the length of y, and this is r for radius if this triangle were in our quadrants. Now this is your 90-degree angle, and I labeled this as theta. Our third missing angle, we know that these two angles here have to add up to 90 or pi over 2. So this angle here should be pi over 2 minus whatever theta is. So the first thing I'm going to do here is write all 6 trig ratios using theta as my reference and then using this pi over 2 minus theta as my reference. I'll start with theta. So here's opposite, adjacent, and hypotenuse. So sine is y over r, cos is x over r, just adjacent over hypotenuse, tan is y over x, and now our reciprocals. R over y, r over x, and x over y. So we're just doing some SOHCAHTOA here, and then reciprocals. I'll do the same thing when I use pi over 2 minus theta as my reference. Now x is opposite and y is adjacent. The hypotenuse is still r. So opposite over hypotenuse will be x over r. Adjacent over hypotenuse will be y over r. Opposite over adjacent will be x over y. And then for my reciprocals, r over x, r over y, and y over x. Now, something that we might notice. This sine ratio is the same as the cos ratio. They're both y over r. So we can conclude that sine theta is equivalent to cos of that complementary angle of pi over 2 minus theta. Likewise, the cos ratio is equivalent to the sine ratio of the complementary angle. So sine of pi over 2 minus theta. And then tan, its ratio is equivalent to its reciprocal. So tan theta is equivalent to cotangent of pi over 2 minus theta. And then the exact same thing for the reciprocals. Cosecant ratio is the same as secant, secant as cosecant, and cotangent as tangent. The ratios are identical. So I will write these out. Now, if we have to think of these complementary angles in terms of quadrants, these would be trig identities specific to quadrant 1. So let's just look at a small sketch here for quadrant 1. And this is my terminal arm. And pi over 2 is here. So this is angle theta. And then when you do pi over 2 subtract theta, this is your other angle that you're looking at. So it's like sine of theta equals cos of this angle here. And this angle here is pi over 2 minus theta, the leftovers from 90. So now let's look at quadrant 2. Let's start off with a diagram for quadrant 2. If my terminal arm is in quadrant 2, this entire angle here is theta. And x is going to be the angle glued to the y-axis. So theta is pi over 2 plus x. And pi over 2 plus x is complementary to x. Now in quadrant 2, only sine is positive. So I expect the sine ratio to be positive, cos and tan to be negative, cosecant to be positive, secant and cotangent to be negative. And now I know sine and cos are complementary, so sine of pi over 2 plus x is equal to cos x. Cos of that angle is equal to negative sine x. And then we know tan is complementary to cotangent, so tangent of this angle is equal to negative cotangent of x. X, again, being that angle glued to the y-axis. And then cosecant is complementary to secant, secant with cosecant, but in quadrant 2, secant is negative, and then cotangent is negative there and complementary to tan. So the relationships are the same. Sine with cos, cos with sine, tan with cotangent, cosecant with secant. It's just that the sign of the ratios will be different depending on your cast rule. So now in quadrant 3, if our terminal arm is in quadrant 3, this entire angle is theta, but x is glued to the y-axis, and that y-axis in quadrant 3 is at 3 pi over 2. So our theta is that entire 3 pi over 2 minus that little x section. And we are now in tan's quadrant. So I will expect sine and cos to be negative and their reciprocals to be negative. But tan and cotangent will have positive ratios. And then the same thing as before, the same complementary connection. Sine with cos, cos with sine, tan with cotangent, but it's going to be positive. Cosecant with secant, secant with cosecant, and cotangent with tangent. And finally, quadrant 4. In quadrant 4, our terminal arm is past 3 pi over 2. And again, our x angle is glued to the y-axis. So theta can be represented as 3 pi over 2 plus x. And now we're in cos's quadrant. So I only expect cos to be positive. And it's reciprocal, so secant will be positive as well. The rest are all negative. And then again, exact same connection as before. So sine will be equivalent to negative cos x. Cos of theta is equivalent to sine of x. Tan of theta is equivalent to negative cotangent of x. Cosecant with secant, and vice versa. And cotangent with tangent, but negative because of the quadrant. So before we do a little example related to these cofunction identities, let's just look at a recap or a comparison of the related angles and the cofunction or correlated identities. So when we are looking at the related angles, we are measuring everything from the x-axis, whereas the cofunction we're measuring from the y-axis. And with that in mind, your related angles will always be with reference to 0, pi, or 2 pi, because that's where the x-axis is. Whereas the cofunction will be related to pi over 2 and 3 pi over 2. When we have related angle identities, the trig ratios are the same. You're comparing a sine ratio in one quadrant with the sine ratio in another quadrant, for example. Whereas for the cofunction angle, the trig ratios are different. And finally, what quadrants are these identities in? So for the related angle identities, we use them in quadrants 2, 3, 4 because everything is with reference to that quadrant 1 ratio, whereas the cofunction can be in all quadrants. So let's try out an example. Express each of the following as correlated angle identities. Well, this is going to start with figuring out what quadrant we're in. So 7 pi over 10 is in quadrant 2. So this angle here from the positive x-axis to the terminal arm, 7 pi over 10. And because we're asked about the correlated angle identity, we know our angle will be with reference to the y-axis. So let's find x first. Now this x value is after pi over 2, and our terminal arm is in quadrant 2. So I need to find the leftovers. So 7 pi over 10, the entire angle, and subtract that first quadrant away, pi over 2, and that will give us x. I will need a common denominator here, so times 5, and I get 2 pi over 10, which reduces to pi over 5. So this is going to be the complementary angle to 7 pi over 10. Now I also know cos and sine are complementary to each other, But we're in quadrant 2, where only sine is positive, which means our cos will be negative. So we're going to have negative sine of the complementary angle. And there we are. Let's try the next one. 3 pi over 10 is in quadrant 1. So this angle here is 3 pi over 10. But our x is glued to the y-axis. So we need to see within that quadrant that's all worth pi over 2. Let's remove 3 pi over 10 to get the leftovers to get our x value. So in quadrant 1, we're doing pi over 2 minus 3 pi over 10, get that common denominator just like before, and subtract. And I get 2 pi over 10, which reduces to pi over 5. And in quadrant 1, everyone is positive. Sine is complementary to cos. So sine of 3 pi over 10 is equivalent to cos of pi over 5. Next we have cosecant of 13 pi over 12. 13 pi over 12 is in quadrant 3. This whole angle here is 13 pi over 12. And our complementary angle is here, glued to 3 pi over 2. So what we're going to do to get x? Well, we know this entire portion here is 3 pi over 2, those 3 quadrants. But our angle stops here. So if we subtract 3 pi over 12 from 3 pi over 2, then we'll get our leftovers for x. And again, common denominator, so times 6. And subtract. And I get 5 pi over 12. And cosecant is the reciprocal of sine, and sine is negative in tan's quadrant. So cosecant of 13 pi over 12 is equivalent to negative secant of the complementary angle. All right, last one. 11 pi over 7 is in quadrant 4. This whole angle is 11 pi over 7, and we know this is x. And that entire angle in quadrant 4 is greater than 3 pi over 2. It surpasses it. So if I want to find x, I'm taking 11 pi over 7 and subtracting 3 pi over 2 from it. And now, once again, common denominator. So times 2 and times 7. And x is equal to pi over 14. And in quadrant 4, tan is negative. So tan of 11 pi over 7 is equivalent to negative cotangent of pi over 14. So with these identities, we need to find that x value, in this case our complementary angle, so that we can then apply our cofunction identity while also keeping in mind our cast rule. And that's it.